Okay, welcome back and hope that you learn a little bit today about the structure of a standard quadratic equation and how that structure affects the graph of that parabola that would be associated with it. So what we're going to do is we're going to take a look at the standard form of a parabola and slowly build in the different components and what that does to the graph. So the parent function is f of x equals x squared, and that one's plotted here. One of the things that I've done is I've created a new function just by adding a constant on. I remember with linear functions what that did is it just created a vertical shift, so I'm believing that's what that's going to do here. And so I plot that function, and indeed it has shifted this point up 3, it's shifted this point up 3, it's shifted this point up 3, and I see that every point has just been shifted up 3. Even though the difference here seems to be decreasing, the width between these is getting different. What that is that's based on the curvature. And if I look simply horizontal in a vertical fashion, what I've got is still a difference of 3 between that and as a constant value. Okay, and if I modify this and say instead of plus 3, I say minus 7 or whatever, well, minus 4 we'll say, so it fits on my screen, then it just does a vertical shift of negative 4 now, down 4. That's pretty basic and straightforward. Let's take a look at a different one. If I put a coefficient on x squared, this might be kind of like it was for the absolute value or for the linear function in adding a coefficient on x. It's just going to squeeze that parabola together, and indeed that's what it does. I'm guessing that if I make it negative, it's going to be going down now instead of going up, and indeed that's what happens. And I'm guessing that if I make it a fraction, such as 1/2, instead of squeezing it together, just like it did for the absolute value function, it's going to stretch it apart. Yes, indeed. So the coefficient on x squared acts as a scale factor in terms of the angle that it makes with the axes. It kind of stretches it or widens it or makes it more narrow depending on the value that you put in. It also can create a vertical reflection um, across the line, horizontal line, vertical reflection that way, in that if the coefficient here is negative, that's what will happen here. Well, now what I've got is something that actually is going to be a little bit of a challenge here. So the parent function is x squared. Now, one of the things that I could do besides um, adding a constant is I could add an x term, just a linear x term. And so I want to take a look at what happens when I add x terms to that. And I've chosen to add even values of x for a specific reason, and you'll see that momentarily. So I'm going to take g of x and I'm going to plot it, and I really have no idea what this is going to do. And isn't that interesting? It seemed to shift diagonally. The vertex was 0, 0. Now the vertex is negative 1, negative 1. Huh. All right, well that's kind of weird. And now I'm going to plot this function. Well, what I have to do is get rid of that one. Now plot that function. And now it shifted it, not in that linear fashion, but it shifted it 2 over and 4 down from the original function. Huh. Weird. Okay. Well, let's plot this one. Plot the function. Well, it's 3 over, and it's 9 down. This is kind of going over, so it goes left, it seems like, and it goes down. Well, it goes left. When it was 2, it went left 1. When it was 4x, it went left 2. And when it was 6x, it went left 3. So when it's 8x, I bet it's going to go left 4. Okay, so let's find out about that. Deselect this, plot the function, and it's at negative 4, it looks like. And yep, it went down there a little bit past the screen. I can scroll down and see that it's at negative 16. Okay. Another thing that's interesting out of that is that it seems to shift the square of half of this value. It's kind of a weird way of putting it, but if it shifted over 5, it would go down the square of 5, which would be 25. That's what it seems to be. Well, one thing I want to do is now play with this a little bit, and instead of adding, let's subtract. And let's see if how that shifts. Now, instead of shifting left, it shifted right. So if that happens here, subtract, and yes, it does. It shifts right. So anytime that I change this to a subtraction, it shifts right. That's kind of like we saw with putting something inside parentheses with a linear function or inside the absolute value. It was the opposite of that value. Okay, well this is pretty challenging to try to figure out exactly how this coefficient on x modifies the graph, but I've got a little bit of an idea here. I want to take a look at putting them all together here. I have not put a coefficient on this one just yet, but what I am going to do is I'm going to plot this function, and it's created a vertical shift of 5 and also this horizontal shift 3 over, because half of this, and then the square of 3 was 9, so 9 down. 9 down and 5 up kind of creates this. I'm got my vertex at -3, -4. Okay, whereas it would have been -3, -9 had the +5 not been there. All right, so that's kind of an interesting thing. Again, if I modify this and I put a coefficient on there, that's just going to squeeze that graph together a little bit. Oh, yeah, and look, that changed the vertex of that one too. Isn't that interesting? So it's not just what's going on here with this, but the A value in addition to the B value. The coefficients here, I'm just going in order, A, then B, then C. The B and the A value both have something to do with that vertical shift. Wow, how is that going to work? I want to go back here and I want to play with this a little bit. So let's go back and let's change this to be a 2, sorry about that, 2x squared. Now instead of shifting over 1, it shifted over a half. Well, instead of doing this as a 2, let's do this as a 4. Instead of shifting over 2, this one also shifted over a half. Let's do this one as a 2 just to see what happens. Instead of shifting over 3, it shifted over 1.5. It seems that I'm creating a ratio here. So I'm going to try 0.5. And in the shift over, instead of shifting over 4, I'm going to guess it's going to shift over 8 now. And I'm going to have to scroll down to take a look and see where that vertex really is. Scroll down quite a bit. There it is. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Indeed, it did shift over 8. So we've got some pretty challenging things to try to think about in transforming a quadratic equation. But for a brief summary, what we've got here, if g of x equals ax squared plus bx plus c, the modification to the parent function f of x equals x squared, a changes the width and direction of the graph. If a is greater than 0, that parabola opens up. If it's less than 0, that parabola opens down. If a is bigger than 1 in terms of its value, its absolute value, that parabola opens more narrowly than the parent function x squared. And if a is less than 1, that parabola opens more widely. B shifts a parabola diagonally, and I'm not really going to get too clear right now on how that shift happens, but what we did notice is if B is less than 0, the parabola shifts right, and it goes up or down some amount depending on the value of A. If B is greater than 0, it shifts the parabola left, and up or down, again, depending on that value of a. Okay, a and b together determine that what's called the line of symmetry, where that graph kind of plays back on itself. So right here I'd have a line of symmetry at looks like -1.5. Going back over here, I have lines of symmetry at 0 on both of these. And going to this one, I have a line of symmetry at x equals 8. Scrolling myself back up. Oops, way too far. Then on this one has a line of symmetry +1.5. This one and this one both have lines of symmetry at +1/2. Okay, that line of symmetry is found by taking the b value and dividing it by twice the a value. That's kind of what we saw with this ratio over here, was that as we played around with this, 2 divided by twice 2 creates a half, 4 divided by twice 4 creates um, the 1/2 again, and if we eliminated that 4, we have 4 divided by um, twice 1, and it creates the line of symmetry at 2. Okay, and so the line of symmetry, as I said, is an x line. It is a straight up and down vertical line, and it's the opposite of the b value divided by twice the a value. Okay, and c, as we saw early on, shifted that parabola vertically equal to that value of c. Okay, hopefully you've learned quite a bit about the um, transformations of a quadratic function. We'll do quite a bit more in terms of a different form of a quadratic function that makes the transformations more understandable and much easier. But understanding a little bit of the structure of what a does to the function in quadratic function, what b does to it, and what c does to it can certainly help you read a standard form quadratic equation in an efficient manner. All right, thank you, and we'll see you.